Biomech Probs, Projectile Motion Equations, a series of Biomech talk. Some backstory on this week's problem. Last time in Biomech Probs, we found jump length and a long jump, and this week I've been reading The Biomechanics of Sports Techniques by James G. Hay, and I'm on chapter 3, which is about linear kinematics, and there's a ton of equations throughout this chapter, including our projectile motion equations, and I keep thinking about where did these equations actually come from and why can we trust them? Why should we care about this? Projectile motion equations can help us find in sports jump distances, time spent in the air, and both initial and final velocity, and all of this information can be found just using video. So these equations are really helpful for understanding sport, but where are they coming from and how are they related to fundamental principles in physics? So for our Biomech problem today, we're going to be deriving the following projectile motion equations. We have 4 equations in both the vertical and horizontal direction, and our variables in these equations are final velocity, which is measured in meters per second, initial velocity, acceleration, which is measured in meters per second squared, time, which is measured in seconds, final displacement, which is measured in meters, and initial displacement measured in meters. To help us stay organized, I'm going to be doing this problem on digital engineering paper and pretending as if it was a homework problem. Our problem statement is that we're going to derive the projectile motion equations, and our assumptions include that the acceleration in the vertical is equal to gravity, which is negative 9.81 meters per second squared, and the acceleration in the horizontal is equal to 0 meters per second squared. We also know that acceleration is equal to change in velocity over change in time, which can be rewritten as velocity final minus velocity initial over change in time. We also know that velocity is equal to change in distance over change in time, which can be rewritten as final displacement minus initial displacement over a change in time. And another property that's important to keep in mind is that average velocity is going to be equal to velocity final plus velocity initial divided by 2. And in place of a figure, we're going to write out our projectile motion equations that we're trying to derive. And now we're ready to start deriving these equations in the vertical and horizontal direction. So the acceleration in the vertical direction is equal to gravity, so basically a force is being applied to the projectile in the air. And in the horizontal, this acceleration is equal to 0 because no force is being applied in the horizontal direction. Then if we go to derive our second equation, basically we're going to rearrange our equation for acceleration by multiplying change in time to the left-hand side, where we end up with velocity final equals velocity initial plus acceleration times change in time. Then if we take this same property over to the right-hand side with horizontal, we can see that when we plug in a 0 for acceleration, we end up with velocity final equals velocity initial. So let's talk a little bit about why this makes sense. Newton's first law is that a body in motion will stay in motion unless acted upon by a force. So our initial horizontal velocity, if for example, could be 10 meters per second, and our initial vertical velocity could be 3 meters per second. And we'll see that our final horizontal velocity will also be equal to 10 meters per second because there's no force acting in the horizontal direction. But our final vertical velocity will not be equal to 3 meters per second because we have the force of gravity acting on the body while it's being a projectile. So we're going to start with what we know about average velocity, which is our formula that we have in our knowns, and we're going to set that equal to our formula for velocity using the displacement terms. Then we're going to rearrange this so we're left with change in time on the left-hand side, which is equal to 2 times the final minus initial displacement over velocity final plus velocity initial. Then we can plug this change in time term into our second equation that we solved for, and then doing some rearrangement using algebra properties that we learned a long time ago, we're going to end up with velocity final squared minus velocity initial squared, which is what we get when we factor out the 2 terms on the left-hand side. And our final equation is velocity final squared equals velocity initial squared plus 2 times acceleration times final displacement minus initial displacement. The same derivation is going to apply in the horizontal direction, but we know that acceleration is equal to 0 meters per second squared in the horizontal, so our term on the right-hand side is going to cancel out, and we're left with the property that velocity final squared is equal to velocity initial squared. Now we're going to combine equations 2 and 3, where we're going to take velocity final, that term from equation 2, and plug it into equation 3, where velocity final is squared. So we're going to end up having to use some basic algebra that we've learned. So we're going to take both of those terms, put them next to each other, and then we're going to have to factor all of that out. And when we do that, we're left with this long term. And then from there, we're able to cancel some information that we have on both sides of our equation. You can see that velocity initial squared is on both sides, so we're going to cancel that out. Then we're going to divide by 2 times acceleration, and then we're left with this equation on the bottom. And if we rearrange so that the final displacement on the left-hand side, we're left with initial displacement plus velocity initial times the change in time, plus 1/2 times the acceleration times the change in time squared. We're able to assume that the same process follows in the horizontal direction, but because the acceleration is equal to 0, that entire term on the right-hand side is going to cancel out, and we're left with final displacement equals initial displacement plus initial velocity times change in time. And our final answer in this situation is that we're going to have our professor see our attached work for the derivation of the projectile motion equations. And here you can see how we derived the 4 projectile motion equations in both the vertical and horizontal directions. And now that we have these equations, we're able to take what we do know about position, velocity, acceleration, and change in time and figure out what we don't know. A series of Biomech talk, Biomech probs, projectile motion equations.